Hello everyone, and welcome back to Tech Adventure. Hope you're doing great and staying sharp in your journey of software development, embedded systems, and interview preparation. In previous videos, we covered I2C, SPI, ADCs, RTOS, top 50 real-world C and C++ interview questions, solid principles, common design patterns, and other key interview Q&A. If you missed them, check out our previous videos, especially the SPI and I2C ones, where we covered detailed differences between SPI, I2C, and UART. Also, a quick correction. In the earlier I2C video, I mentioned 10-bit addressing supports up to 123 slaves. I meant it can support up to 1023. See here. For 7-bit addressing, the maximum is 128 addresses. Today's topic is UART, another widely used microcontroller communication protocol. We'll explore its working, frame details, and applications in detail while covering key interview questions. Let's dive in.
Okay, let's unpack this. Think about the tiny chip inside your smart doorbell talking to your Wi-Fi maybe, or a weather sensor sending data back home. It's not just information flowing one way, is it? It's like these constant hidden conversations happening all around us. But how do these really small, complex bits of hardware actually talk to each other? What's the basic language, the hidden one that powers so many devices? Today, we're diving deep into something really fundamental in embedded systems, UART communication. It's this simple but actually quite powerful way microcontrollers connect to all sorts of things, sensors, your computer, you name it. Our mission here is to decode UART, that's Universal Asynchronous Receiver Transmitter, and make it really simple, clear, easy to understand. By the end, hopefully you'll get why it's important, how it's used, and maybe see those little device interactions in a new light.
Absolutely.
Yeah.
And it really is crucial stuff. You're curious about how devices connect. Understanding these basics, it's like learning the alphabet, Suddenly, much more complex topics start making sense. UART is just everywhere. Knowing how it works, it demystifies a huge chunk of modern electronics. Shows the clever simplicity behind it all.
That's a perfect analogy. Okay, so let's start right at the beginning then. What is UART and why the asynchronous part? What does that mean?
Right, so UART stands for Universal Asynchronous Receiver Transmitter. At its heart, it's a communication protocol, basically, a set of rules letting two devices swap data, usually one byte at a time. Think of it like a direct line, maybe, between a microcontroller and, say, a sensor. Or even a small computer.
Okay, a direct line. Makes sense.
And universal just means it's pretty adaptable, works with lots of different devices. But asynchronous, that's where the real clever bit is. It means there's no shared clock signal between the sender and receiver.
Shared clock. How do they stay in sync then?
Well, that's the thing. Instead of a clock wire, they just agree beforehand on a speed. It's called the Baud rate. That's just how many bits per second they'll aim for. Then each device uses its own internal clock to time the sending and receiving of each bit. The sender just starts sending, and the receiver listens, timing the incoming bits based on that agreed speed. Its simplicity is why it's so popular for, straightforward short-distance links.
Right, simpler setup, fewer wires, got it. But I sometimes hear USART mentioned too, USART. Tiny name difference. Is it a big functional difference?
Yeah, good question. It's subtle in name, but definitely significant in what it can do. UART, like we said, is only asynchronous. It banks entirely on that timing agreement, the start-stop signals, no extra clock line. Great for talking to GPS modules, Bluetooth, simple debugging, that kind of thing.
Okay.
USART, though, stands for Universal Synchronous Asynchronous Receiver Transmitter. So it can do everything UART does run in asynchronous mode, but it also supports synchronous communication.
Synchronous, so that does use a clock.
Exactly. In synchronous mode, you add a dedicated clock line. One device becomes the master, sends the clock signal. This syncs the data bit for bit, which means you don't need start and stop bits anymore. You can send data continuously, and that often means much faster data rates are possible.
I see. So USART is more flexible, but maybe a bit more complex to set up.
Precisely. It's like a superset. If you have a USART peripheral, you can often just configure it to act like a plain old UART. A lot of microcontrollers, like the STM32s, have USART peripherals, but you just use them in asynchronous mode for standard UART communication.
Okay, that clarifies the difference. So when I'm actually wiring things up, what are the absolute essential connections? Just the bare minimum.
For basic UART, you really only need 3 wires. You need TX transmit for sending data out of your device, RS receive for bringing data in, and crucially, G&D ground. This is the common electrical reference. Without it, the devices won't agree on what's a high or low voltage.
Right, the common ground. Easy to forget, I bet.
Oh, definitely. That's a super common pitfall. Forgetting ground or connecting TX to TX and RX to RX.
Oh, right. It needs to be crossed over, doesn't it?
Exactly. TX from device A goes to RX on device B, and RX on A goes to TX on B. Always cross them.
Okay, TX to RX, RX to TX, and don't forget ground. Got it. So we know the basics now, but where does this actually show up? What are some everyday applications?
Oh, you are surprisingly common, especially in the embedded world. Debugging is a huge one. If you're writing code for a microcontroller, you'll constantly use UART to send messages, like variable values or status updates, back to your PC. It's how you see what's going on inside.
Right, the classic print statement debugging, but over serial.
Exactly that.
Right.
It's also vital for talking to external modules. Think GPS modules, Bluetooth chips, maybe some Wi-Fi modules. Many of them use UART to communicate with the main processor. And another big one, firmware updates. Lots of microcontrollers have a built-in UART bootloader.
A bootloader, what does that do?
It's a small program that runs first, allowing you to update the main software on the chip just by sending the new code over the UART connection from your computer. Super handy. Its popularity really boils down to that simplicity. Just a few wires, easy to implement.
Sounds incredibly useful, but you mentioned it's a direct line. Does that mean I can only connect 2 devices? Can you have like 3 or 4 devices talking on the same UART lines?
No, not really. UART is inherently point-to-point. It's designed for a direct conversation between only 2 devices at a time. One sender, one receiver on a given pair of TX-RX lines. If you need more devices sharing the same communication bus, you typically look at other protocols. Things like ICOTA-C or maybe RS-485 are better suited for that multi-device setup.
Okay, point to point. Got it. So back to the asynchronous part. If there's no shared clock, how does the receiver know when a new byte starts or ends? How is the data actually structured or framed?
Good question. That's where the concept of the UART frame comes in. Data isn't just sent as a raw stream of bits. Instead, each chunk of data, usually a byte, gets packaged into a structured group of bits, a frame. A typical frame has a very specific structure. It starts with a start bit.
Okay, a start signal.
Right. Then come the actual data bits, the information itself. After that, there might be an optional parity bit for basic error checking. And finally, it ends with 1 or maybe 2 stop bits.
So start, data, maybe parity, stop. What do those actually look like electrically?
The start bit is always a transition to a low W state, like a logical 0. The line is usually idle HHH, so when the receiver sees it drop LOW, it knows, okay, data's coming, and starts its timing. The data bits follow, usually 8 of them for a standard byte, but it can be configured from 5 to 9 bits. The optional parity bit is calculated based on the data bits for that simple error check. We can touch on that more later. And the stop bits are always IGH, logical 1. They signal the end of the frame, telling the receiver that byte is done, and it guarantees the line goes back to idle high before the next potential start bit. Usually 1 stop bit, sometimes 2 for a bit more breathing room.
And you mentioned a common format, 8N1.
Yes, exactly. 8N1 is probably the most common configuration you'll encounter, it means. 8 data bits, no parity bit, and 1 stop bit. So for every 8 bits of actual data you want to send, you actually transmit 10 bits over the wire. 1 start bit, 8 data bits, and 1 stop bit.
10 bits for an 8-bit byte. Okay, what about other formats?
Yeah, there are others. You might see 7E2, that's 7 data bits, even parity, 2 stop bits, or maybe 801, 8 data bits, odd parity, 1 stop bit. The nomenclature is pretty straightforward. Data bits, parity type, M for none, E for even, O for odd, and stop bits. The choice depends on the device you're talking to and whether you need that basic parity error checking.
And the order of those data bits within the frame, does it send the most significant bit first, or?
Good point. By default, UART sends data least significant bit first, LSB first. So if your byte is, say, 0B10110011, the first bit actually sent over the wire after the start bit would be the rightmost one, then the next one, then 000, and so on, up to the leftmost, which is the most significant bit, MSB. Knowing it's LSB first is important if you're ever trying to decode the raw signals yourself.
Okay, LSB first. Now, we've mentioned baud rate a few times, the speed. Can we dig into that? How does it relate to the frame structure and the whole communication process?
Absolutely. Baud rate is the heartbeat, really. It defines the speed specifically, how many signal changes or effectively bits are sent per second. So 9600 baud means 9600 bits fly across the wire every second. If you're using that 8N1 format, which takes 10 bits total per byte, well, 9600 bits per second means you can send 960 bytes of actual data per second. The absolute crucial thing, though, is that both device's sender and receiver must be configured for the same baud rate, or at least incredibly close.
Right. What happens if they're not? Say, one set to 9600 and the other accidentally to, like, 150, 200.
Oh, you just get garbage. Complete nonsense. If the rates don't match, the receiver samples the incoming signal at the wrong moments in time. It misinterprets the bits.
Yeah.
You'll see garbled characters on your terminal, maybe miss bytes entirely. It just won't work. Communication breaks down completely. It's like trying to listen to someone speaking way too fast or way too slow. You can't understand them. Matching baud rates is non-negotiable.
Absolute necessity. Got it. How is that rate actually set inside the chip? How does a microcontroller generate, say, exactly 9600 bits per second?
Microcontrollers usually generate the baud rate using their main system clock and some clever hardware dividers. There's typically a specific register, like the USART BRR register on an STM32, for example. You write a calculated value into this register. This value tells the internal hardware exactly how much to divide the main system clock, which might be running at many megahertz, down to get the precise timing needed for the desired baud rate, like 9600 or 11.152.200.
So it's derived from the main clock. Are there standard rates people usually use?
Yes, there are definitely common baud rates. You'll often see 9600 that's kind of a classic, often used for simple debugging. The 19200, 380, 400, 57600, and a 15200 are also very common. 1015200 is quite popular for faster communication that's still widely supported. You can even go much higher, into the megabits per second range on some devices, but compatibility might become more of an issue. And accuracy is key. The generated rate usually needs to be within about 2% in the target rate for reliable communication. Any more deviation, and you risk those sampling errors creeping in. That's why stable clock sources, like crystal oscillators, are often important.
Okay, so accuracy matters a lot. If things do go wrong, besides baud rate mismatches, what other kinds of errors can pop up in UART? How do we even know our data arrived okay?
Right. Communication isn't always perfect, especially in the real world with electrical noise and all that. Several common errors can occur. You can get a framing error. This usually happens if the receiver doesn't detect the stop bit where it expects it, often caused by, baud rate mismatch or maybe noise corrupting the signal right at the end of the byte. The receiver basically loses sync with the byte structure.
Okay, flaming error. What else?
If you're using parity checking, you can get a parity error. This means the number of 1 bits received plus the parity bit itself doesn't match the expected parity, even or odd. It tells you at least 1 bit probably flipped during transmission. Then there's overrun error. This happens if new data arrives from the sender before the receiver has finished reading the previous data from its internal buffer. The buffer overflows and the new data is lost. Essentially, the receiver couldn't keep up. And just general noise error, where electrical interference flips bits randomly. Microcontrollers usually have status flags you can check to see if any of these errors have occurred.
You mentioned parity again. How does that actually work to detect an error? Is it reliable?
Parity is a pretty simple form of error detection. When it's enabled, you add 1 extra bit to each data frame. If you choose even parity, the sender calculates the parity bit so that the total number of 1s in the data bits plus the parity bit is an even number. If you choose odd parity, the total number of 1s must be odd. The receiver does the same calculation on the data bits it receives. If its calculated parity doesn't match the parity bit that was sent, it flags a parity error. The big limitation, though, is that it can only reliably detect an odd number of bit errors. So it catches single bit errors fine. But if 2 bits flip, the parity might look correct again, and the error goes undetected. It also can't correct any errors, only detect some of them.
So it's a basic check, but not foolproof for multiple errors. If an error is detected, or if maybe a whole chunk of data just gets lost, how do you typically recover or even notice the loss?
Good question. Recovery often involves a few layers. If an error flag is set, you might just flush the receive buffer to discard the potentially corrupted data and wait for the next valid start bit to try and resynchronize. For more robustness, you often build error handling into your communication protocol on top of UART. This might involve retries. The receiver asks the sender to resend the packet if it detects an error or doesn't receive it within a certain time. Using checksums, or even better, CRC, cyclic redundancy check, is common. These involve calculating a value based on the entire data packet. The receiver does the same calculation. If the checksums don't match, you know the data is corrupt. CRC is much more powerful than parity at detecting multiple bit errors.
So checksums help verify the data you received. What about detecting data that just never arrived? Lost packets.
Right, for lost data detection, a few techniques work well. Sequence numbers are great. The sender includes a counter in each packet. If the receiver gets packet 1, then packet 3, and knows packet 2 was lost. Timeouts are also essential. If the receiver is expecting data, maybe as part of a request response, and nothing arrives within a set time limit, it assumes the data was lost and can request a resend or take other action. Sometimes protocols use acknowledgments, ACK and AEK. The receiver explicitly sends back a small message, ACK, to confirm it got a packet OK, or an AEC if it was corrupted or not received. If the sender doesn't get an ACK, it resends. Combining these methods gives you pretty robust communication.
It sounds like managing the flow of data is really important, especially if one side might be faster than the other or has limited buffer space. You mentioned that analogy of someone talking too fast. How does UART handle that?
Flow control, right.
Exactly. Flow control prevents the sender from overwhelming the receiver. There are 2 main types we talked about briefly. First is hardware flow control, which uses 2 extra wires, RTOS, request to send, and CTS, clear to send. RTOS and CTS, how do they work?
It's like a handshake. The device that wants to send data asserts its RTOS line, basically saying, hey, I want to send. The receiving device will only assert its CTS line when it's actually ready to receive data, e.g., its buffer has space. The sender must check that the receiver's CTS line is asserted before it starts transmitting data. If CTS drops, the sender pauses. It's a very direct, hardware-level way to manage the flow and prevent buffer overflows. Very reliable.
Okay, hardware uses extra wires. What's the alternative?
The alternative is software flow control, often called XON XOFF. This method doesn't need extra wires. Instead, it uses special control characters sent over the main TXRX data lines. When the receiver's buffer is getting full, it sends a specific character, usually XOFF, stands for transmit off, often ASCII code 0x13, back to the sender. The sender sees this XOFF character and pauses its transmission. Once the receiver has processed some data and has space again, it sends an XON character, transmit on, often 0x11, telling the sender it's okay to resume.
Ah, so it uses the data channel itself. When would you choose one over the other? When is flow control actually needed?
You typically need flow control when you're sending large amounts of data, especially continuously, like transferring a file or streaming sensor readings at high speed. It's also crucial if the receiving device has a very small input buffer, or might be busy doing other things and can't always service the UART instantly. Hardware flow control, RTOS, is generally more robust and reliable because it's out of band, uses separate wires. Software flow control, XO and XOF, is useful when you don't have those extra pins available, but it does consume a tiny bit of bandwidth for the control characters and relies on those characters not appearing in the actual data stream, or needs escaping mechanisms. Basically, use it whenever there's a risk of the sender transmitting faster than the receiver can process to prevent data loss and ensure stability.
Makes sense. Let's shift gears a bit to the physical layer again, the actual electricity. What are the common voltage levels for UART? Does it always run at, say, 5 volts?
No, definitely not always 5 volts. Voltage levels are critical, and mismatching them is a common way to damage things. The most common type you'll find inside modern electronics, especially with microcontrollers and sensors, is TTL UART. This typically uses logic levels of either 3.3 volts or 5 volts. Then there's the older RS-232 standard. This uses much higher voltages, often swinging between positive and negative 12 volts, sometimes more or less. You find this on older PC serial ports and some industrial gear. And for really long distances or noisy environments, there's RS-485, which uses differential signaling, 2 wires carrying opposite signals, which makes it very noise resistant. It operates at different voltage levels again. The key takeaway is, you must know what voltage level each device uses and ensure they are compatible or use a converter.
Okay, so TTL and RS-232 are very different. You mentioned converters. How exactly do you connect, say, a 3.3V microcontroller TTL to an old computer with a 12V RS-232 port?
You absolutely need a level shifter IC, like the classic MX232 chip or one of its many modern equivalents. These chips do 2 crucial things. First, they convert the voltage levels, for example, 0V, 3.3V from the microcontroller to maybe plus minus 10V for RS-232 and vice versa. Second, they handle the logic conversion. Remember, TTL logic is typically IGH equals 1, LOW equals 0, but RS-232 is often inverted. A positive voltage means logical 0, and negative voltage means logical 1. The level shifter flips the logic appropriately. You cannot connect them directly. You'll either get no communication or worse, damage the lower voltage device.
Right, the dreaded magic smoke. And what about connecting, say, a 5V device to a 3.3V device? Both are TTL, but different levels.
That also needs care. Connecting a 5V output directly to a 3.3V input can damage the 3.3V chip unless that specific input pin is explicitly rated as 5E tolerant. If it's not 5E tolerant, you need a simpler logic level converter or even just a voltage divider using resistors on the 5V output line to bring the voltage down to a safe level for the 3.3V input. Going the other way, 3.3V output to 5V input often works okay, as 3.3V is usually high enough to be read as a logic HEH by a 5V device, but it's always best to check the datasheets.
Always check the datasheets. Good advice. What about distance? We talked about protocols like RS-485 for long runs. How far can standard TTL UART typically go?
Standard TTL UART, the kind directly from microcontroller pins, is really meant for short distances. Think connecting chips on the same circuit board, or maybe across a cable of perhaps 1 to 2 meters maximum under ideal conditions. If you need more distance, RS-232 can typically manage up to around 15 meters, maybe a bit more, depending on the baud rate and cable quality. But for genuinely long distances across a room, a building, or even further, up to 1,200 meters, RS-485 is the way to go. Its differential signaling is much better at rejecting noise picked up over long cables. And for any longer cable run, regardless of the standard, using shielded cables and twisted pairs for the signal lines is highly recommended to minimize noise interference.
Okay, that gives a good sense of the physical constraints. Let's dive into the firmware side for developers. How do you actually configure UART on a specific microcontroller, say an STM32?
Sure. On something like an STM32, you typically start by configuring the peripheral settings. This involves setting the core parameters we've discussed, the baud rate, read to 115-200, the word length, usually 8 bits, parity, none, even or odd, and the number of stop bits, 1 or 2. You often use a graphical configuration tool like STM32CubeMX, which makes this pretty easy. You select the settings and it generates the initialization code for you. Under the hood, this generated code, often using the HAL hardware abstraction layer library, writes specific values to the microcontroller's internal registers, like the USART BRR for baud rate, and control registers, USART CR1, CR2, CR3, for enabling the UART, setting word length, parity, stop bits, and maybe enabling features like DMA or flow control.
You mentioned DMA again. We touched on it, but can you elaborate on how DMA specifically helps with UART and why it's so beneficial?
All right, DMA Direct Memory Access is a fantastic feature for efficient UART communication. Its core benefit is allowing data to be transferred directly between the UART peripheral's data register and a buffer in memory without any intervention from the main CPU. So when a byte arrives at the UART receiver, the DMA controller can automatically grab it and place it into your designated memory buffer. Similarly, for transmitting, DMA can automatically feed bytes from a memory buffer to the UART transmitter. This means the CPU doesn't have to respond to an interrupt for every single byte received or transmitted. It frees up the CPU to do other more important tasks. The result is much higher potential throughput, lower CPU load, and it's especially ideal for handling continuous streams of data or operating at high baud rates where byte-by-byte interrupts would overwhelm the CPU.
So it really takes the load off the CPU. Now, often the data you send isn't just single bytes, but packets, right? And maybe those packets aren't always the same size. How do you handle variable length packets over UART?
Yeah, that's a very common scenario. You need a way for the receiver to know where one packet ends and the next begins, especially if they vary in size. There are several standard techniques. One, start and end markers. Use special unique byte values that won't appear in your normal data to signal the start and end of a packet. For example, maybe 0xAA starts a packet and 0x55 ends it. The receiver looks for this sequence. 2. Length field. Include a byte or two near the beginning of the packet that explicitly states the length of the data payload that follows. The receiver reads the length first, then knows exactly how many bytes to expect for the rest of that packet. 3. Timeouts. You can use interbyte timeouts. If the receiver is getting bytes for a packet and then suddenly there's a pause longer than a predefined threshold, it assumes the packet is complete or possibly corrupted. This is often used in conjunction with other methods. Often a robust protocol combines these. A common structure might look like start byte length, byte nest, data payload, checksum CRC, end byte.
So you're essentially defining your own mini protocol on top of the basic UART byte stream. Could you walk through designing a super simple custom protocol like that?
Absolutely. Let's build on that structure. Say we want to send a command with some data. 1, start byte. Let's pick 0xAA. Always start a packet with this. 2, length byte. The next byte tells us how many bytes are in the payload section only. 3, payload. This is the actual command in this data. Could be 1 byte, could be 20. 4, checksum. A simple checksum, maybe just the sum of all the payload bytes, modulo 256, so it fits in 1 byte. For basic error checking. 5, end byte. Let's use 0x55 to mark the end. If everything matches, the packet is valid.
That makes it much clearer how you build structure. Okay, let's talk troubleshooting. Things inevitably go wrong sometimes. What are the essential tools for debugging UART issues?
Oh yes, debugging UART can sometimes feel like black magic if you don't have the right tools. The number one most helpful tool is probably a logic analyzer. This device captures the actual digital signals on the TX and RX lines over time. It lets you see the bits, the start-stop bits, the timing. You can instantly diagnose problems like incorrect baud rates, framing errors, or check if data is being sent at all. Indispensable for low-level issues. An oscilloscope can also be useful, especially for looking at signal quality, noise issues, or checking voltage levels are correct. Is it really 3.3D or is it noisy? For interacting with the device from your PC, you absolutely need serial terminal software. Programs like PuTTY, TeraTerm, RealTerm, or CoolTerm. They let you open the serial port, send characters to your device, and see the characters your device sends back. Essential for testing firmware, sending commands, viewing debug messages. And, of course, you need a way to connect your microcontroller's TTL UART pins to your computer's USB port. That requires a USB to UART converter module. Common chips used in these are FTDI, FT232HAR, Silicon Labs CP2102, or WCH CH340.
Logic analyzer sounds powerful, but maybe not everyone has one. Are there simpler ways to test if UART is working at all without specialized hardware?
Definitely. You can do some basic sanity checks pretty easily. The simplest is probably the loopback test. Disconnect anything else from your microcontroller's UART TX and RX pins, and disconnect the TX pin directly to the RX pin on the same chip. Then write firmware to send some data out the TX pin and immediately try to receive it back on the RX pin. If you receive exactly what you sent, you know the UART peripheral itself, and your basic send receive code is likely working.
Ah, clever. Talking to yourself.
Exactly. Another easy check is using that serial terminal software on your PC with a USB to UART adapter. Write simple code on your microcontroller to just print a message like "Hello World" at the UART when it starts up. If you see that message appear correctly in your terminal with matching baud rates, TX is working, then maybe add code to echo back any character it receives, type something in the terminal, see if it comes back. That tests RX. Even simpler, you could just blink an LED inside the UART and see interrupt or after successfully receiving a specific character. Send the character from your PC, see if the LED blinks. It's basic, but confirms data is arriving.
good practical tips. Noise is always a potential issue in electronics. How can you minimize noise-corrupting UART signals, especially over slightly longer wires?
Noise is a constant battle. A few best practices really help. 1. Use twisted pair wires. For the TX and RX lines, twisting them together with a ground wire helps significantly cancel out induced electromagnetic interference. 2. Use shielded cables. For longer runs or really noisy environments, a cable with an overall shield connected to ground provides an extra barrier against external noise. 3. Ensure proper grounding. A solid, low-impedance ground connection between the devices is crucial. Ground loops or poor grounding can cause all sorts of weird issues. 4. Keep wires short. The shorter the wires, the less chance they have to act as antennas picking up noise. 5. Route away from noise sources. Keep UART wires physically separate from high-power lines, switching power supplies, motors, relays, etc. 6. Add bypass capacitors. Small capacitors, like 100 NF, placed close to the power pins of the chips involved, can help filter out high-frequency noise on the power supply, which can sometimes affect logic levels. And as we mentioned, if noise is a major problem or distances are long, switching to a more robust standard like RS-485 might be the best solution.
Okay, lots of good techniques there. How would you typically test communication specifically between a PC and a microcontroller, step by step?
Okay, testing PC to MCU UART. 1. Connect your USB to UART adapter to the PC's USB port. Make sure drivers are installed. Note the COM port number it gets assigned. 2. Connect the adapter's G&D pin to the microcontroller's G&D. 3. Connect the adapter's TX pin to the microcontroller's RX pin. 4. Connect the adapter's RX pin to the microcontroller's TX pin. Remember the crossover. 5. Open your serial terminal software on the PC. Select the correct COM port. Configure the baud rate, data bits, usually 8, parity, usually none, and stop bits, usually 1, to exactly match the settings programmed into your microcontroller firmware. 6. Run the microcontroller firmware. Have it send a startup message like MCU ready. Check if this appears correctly in the terminal. This test MCU TX-PCRX7. In the terminal software, type a character or a test message and send it. Have your microcontroller firmware programmed to receive UART data and maybe blink an LED or, even better, echo the received character back to the terminal. 8. Check if the LED blinks or if the character you typed appears back in the terminal. This tests PCTX-MCURX-MCUTX-PCRX. Full loop. If both steps 6 and 8 work, your basic communication link is functional.
Perfect checklist, thanks. One last specific piece of jargon, UART bootloader. We touched on it for firmware updates. Can you explain that a bit more?
Sure. A UART bootloader is a small, special piece of firmware that usually resides in a protected area of the microcontroller's memory, like the very beginning of flash or in dedicated ROM. Its main job is to run before your main application code starts. When the chip powers up or resets, the bootloader runs first. It typically checks if there's a command coming in via the UART port requesting a firmware update, or sometimes checks a specific pin state. If it detects an update request, it takes control and manages the process of receiving the new firmware image over UART using a specific protocol and writing it into the main application area of the flash memory, erasing the old code. If no update request is detected after a short timeout, it simply jumps to the start of your main application code and lets it run as normal. The big advantage, as we said, is that you don't need a specialized hardware programmer, like a JTAG or SWD probe, to update the firmware in the field. You can just use a simple USB to UART adapter and software on a PC. Many microcontrollers, like STM32s, come with a factory-programmed UART bootloader built in.
Very convenient. Okay, focusing back on the firmware code itself, how do you actually send and receive data in C, for example, using the STM32 HAL library functions?
Yeah, the HAL library makes it pretty straightforward. Once you've initialized the UART peripheral using hello R tenant, which sets up baud rate, etc., often generated by CubeMX, you have functions for sending and receiving. To send data, you typically use hello R transmit. You give it a pointer to your UART handle, like in the short 1, a pointer to the data buffer you want to send, usually be an array of bytes, the number of bytes to send, and timeout value. Example, hello R transmit no word 1, MSG, size of MSG, 100. Sinus 1 allen 1 avoids sending the null terminator of the C string. To receive data in a simple blocking way, you use hello R to receive. You give it the UART handle, a pointer to a buffer where the received data should be stored, the maximum number of bytes to receive, and a timeout. The function will wait until it receives that many bytes or the timeout expires. Example, UART buffer 10. Hello UART receive and UART 1 buffer 10 500, wait up to 500 meters to receive 10 bytes. There are also non-blocking versions using interrupts, hello UART transmitted, hello UART receive, and DMA, hello UART transmit and DMA, hello UART receive divas, which are more efficient for most real applications as they don't make the CPU wait.
Those DMA and interrupt versions sound essential for efficiency. When you're receiving data, especially continuously, how do you manage the buffers? You can't just use a small fixed buffer, right?
Exactly. For receiving data, especially if it's arriving asynchronously or in bursts, using a simple fixed buffer with how you UART receive can lead to problems like blocking the CPU or losing data if it arrives while you're processing the previous chunk. The standard, much better approach is to use a ring buffer, also called a circular buffer. Imagine it as an array, but with 2 pointers or indices. A head where new data is written by the interrupter DMA, and a tail where your main application reads data from. When the head reaches the end of the array, it just wraps around back to the beginning. Same for the tail. This allows the receiving mechanism, ISR or DMA, to continuously stuff incoming bytes into the buffer without stopping, while your main code can pull data out at its own pace from the tail end. You just need logic to check if the buffer is empty, head equals tail, or full, head is right behind tail after wrapping. This structure is perfect for decoupling the high-speed arrival of data from the potentially slower processing of that data in your main loop or tasks. You typically use the IT or DMA or C functions to constantly fill this ring buffer in the background.
Ring buffer, right? Makes sense for handling streams. How does that DMA plus ring buffer combination work for continuous streaming?
That combo is really the gold standard for high throughput, low overhead UART reception. You configure the how UART receive DMA function to continuously receive data directly into your ring buffer. You tell the DMA controller the start address of the buffer and its total size. The DMA hardware will then automatically grab each incoming byte from the UART and write it to the next available spot in the ring buffer. Because you configure the DMA in circular mode, when it hits the end of the buffer, it automatically wraps around to the beginning and continues writing. Your main application code then just needs to periodically check the DMA's current write position, which corresponds to the ring buffer's head against its own tail pointer where it last read up to. If the head is moved ahead of the tail, it knows there's new data available in the buffer between tail and head, handling wraparound logic carefully. It reads the data, updates its tail pointer, and goes back to doing other things. The CPU is only involved in occasionally checking the pointers and processing the data in chunks, not handling every single byte. It's incredibly efficient for things like logging sensor data or receiving large files.
That sounds very powerful. One last area. How does all this fit into a real-time operating system, an RTOS, like FreeRTOS? Does that change how you handle UART?
Yes. Using an RTOS adds another layer of structure and generally makes managing communication like UART cleaner, especially in complex applications. Instead of processing data directly in your main loop, you typically have a dedicated RTOS task whose sole responsibility is handling UART communication, or perhaps just receiving. The UART receive interrupt, ISR or DMA completion callback, would do the absolute minimum work, usually just grabbing the received byte and putting them into an RTOS queue. That dedicated UART task would spend most of its time blocked waiting for data to appear in the queue, using something like receive. When the ISR puts data in the queue, the RTOS automatically unblocks the UART task. The task then reads the data from the queue, processes it, parses packets, acts on commands, etc., and then goes back to waiting on the queue. You might also use RTOS semaphores to signal data readiness between the ISR and the task. This approach keeps your ISRs very short and fast, critical in an RTOS, prevents UART handling from blocking other important tasks, and neatly encapsulates the communication logic within its own task, making the whole system more organized and responsive.
Wow, what an incredible journey through UART. We've really covered a lot, from the absolute basics of asynchronous communication, the frame structure, baud rates, all the way to DMA, ring buffers, custom protocols, and even RTOS integration. It really strikes me how this seemingly simple, often just three-wire protocol is such a fundamental building block. It enables so many devices around us to just talk.
Indeed. And what's fascinating, I think, is the contrast. On the surface, UART looks simple: connect a few wires, set a speed, send bytes. But as we've seen, getting it right requires careful attention to those details: the framing, the exact timing, handling potential errors, managing the data flow. If any of those are off, things just don't work reliably. It really raises an interesting question, doesn't it? If even this relatively straightforward serial protocol has these critical nuances and relies on unseen agreements like matched baud rates, imagine the layers upon layers of complexity involved in the high-speed wireless communication like Wi-Fi or Bluetooth that we often just take for granted.
That is a really powerful thought. Yeah. So the next time you use a smart device, or maybe even just see a simple sensor connected somewhere, hopefully this deep dive gives you a different perspective. Think about those hidden conversations, the start bits firing off, the stop bits marking the end, the perfectly matched timing, all that silent chatter happening constantly in the background. It really makes you appreciate how much of our connected world relies on these fundamental protocols like UART just to be able to talk to each other.
Thank you for watching. Please like, share, and subscribe to our channel for more exciting updates. Your support motivates us to create valuable content. Share your feedback or topic requests in the comments. See you in the next deep dive interview session.